Good afternoon, everyone. So this session is on troubleshooting segment routing. My name is Luc Degain. I'm a principal engineer in CX out of the Brussels office. More specifically, I spent the better part of my life in the tech. A couple of housekeeping things. Do you hear an echo or is it just me? It's fine? Not so good? Yeah. Can you fix it? I hear the echo myself as well. I guess I need to keep talking. All right, so a couple of housekeeping things. It's a big room. So anybody beside after the third row, if you have a question, I will not hear it. There's no way. And walking back and forth, that will take too much time. So please, if you have a question in the back, keep it for the end. Come to me after the session, or put it in the WebEx, and in the coming days or hours, I will try to answer it. The front row, maybe I will take some questions, time permitting. So this is the agenda. We'll do yet another segment routing MPLS recap, and then the troubleshooting part, SR-V6, microSID as well, recap, and a part of troubleshooting. Another look at Ti-LFA, the protection, and then a bigger part on specifically the SR policy, or SRT, traffic engineering. And finally, some troubleshooting examples. I took some tech cases that we worked on the last year, and I took some examples from there and gave you about 10 examples what to look at and how to troubleshoot. I do hope you looked at the abstract. It did mention that you have to be somewhat familiar with segment routing. I will not start from from zero, but let's do a recap anyway. All the output, all the commands, etc., are from iOS XR. That doesn't mean that the theory is not applicable to the other operating systems as well, right? It's the same there. Of course, the commands will be somewhat different. And if you want to stay up to date, this is really a great page to look at, segmentrouting.net. I think it has everything you need. All right, so segment routing is about segments, getting the packets from A to B, and that across a path. That path will be made up of segments, one or more segments. And if you look at SR-MPLS, which came out first, one segment is really one MPLS label. That's it. Later on, we have SR-V6, which is based on IPv6, of course, where one segment, maybe two, but one segment is an IPv6 address. And later on, building on top of SR-V6, we said, hold on, we can put different segments even in one IPv6 header because we have 128 bits, which is a lot. But now you have two choices, MPLS world, IPv6 world. Right? MPLS forwarding, IPv6 forwarding. Let's have a look at SR-MPLS first. There are two things you really need to know. So we will look at SIDs, segment identifier. In the MPLS world, that's an MPLS label, of course. Two important things is, one, prefix SID. This is the identifier of a router, and it's globally unique. So it will be a label, a number, a label, attached to the loopback of one router. And it's globally unique, so you cannot make any mistakes in the configuration. And you see a command there to check that range where we will take those prefix SID labels from. Typically, by default, it's 16,000 to 24,000 minus 1. So 8,000 labels, plenty of choices. So that's one label, one prefix SID per router. Pretty simple. And what is the purpose of a prefix SID? It's a segment. It's to get the packet to a router. That's it, to an endpoint. We also have adjacency SIDs. Those SIDs will be linked to an interface. Right? So per router, and it will be dynamically, unless you really want to override it. But dynamically, the router will allocate an MPLS label, a SID, an adjacency SID, to one interface. This is to get the packet, once you're on that router, across an interface to the next hop router. It's always one hop. Prefix SID could be one hop or multiple hops when you look at the forwarding. And for the adjacency SIDs, those labels, we in the MPLS world, will be taken from the dynamic range, right? It used to be starting at 16, ending at 1 million and a bit. But as you will see, some other ranges nibbled a bit of the labels there. Now the dynamic label range will typically start at 24,000. Recap on the forwarding. We want to get packets from A to B. It could be in a VRF context or not, IPv4, IPv6, EVPN, so layer 2 traffic, it doesn't matter. But we have a service. The service could be L2 VPN, L3 VPN, 6PE, etc. Whatever it is, typically assisted by BGP. The network is kind of carved up by all possible segments, and there are a lot of segments here. One of the things we want to do with segment routing is traffic engineering or source routing. We want to get the packet from PE1, ingress PE, to PE2, egress PE, possibly along a specific sourced path, not necessarily the shortest path. And we can do that by using the segments we just covered. On the one hand, every router will advertise one prefix SID, and it will also advertise an adjacency SID, one per interface, a label. In the end, all of this will be flooded, advertised by the IGP, ISIS or OSPF. It has to be a link state protocol, otherwise it won't work. It's source routing, traffic engineering, so every router needs to have a complete view of the topology of every router in an area, possibly the domain. Otherwise it will not work. So in the end, we have every router's advertising their specific prefix SID. Okay, in this case, we will look at the endpoint of the first segment, which is P3. It will advertise a label which is associated with its loopback. P2, which is the endpoint of another segment, will do the same. But now we want to make sure that the traffic crosses one link, the link P3 to P6. For that, we're going to use the adjacency SID, or the adjacency MPLS label, which is dynamically assigned by the router P3. Okay. So we will have 3 segments, a segment from P1 to P3, P3 to P6, and P6 to P2. All right? And you can see the prefix SID, to get the packet to the endpoint there, the first segment, P3, can be multiple hops. Then we have a segment 1 hop, and then we have a segment multiple hops again. Again, it's a prefix SID, can be multiple hops. In the end, the ingress router has a complete view of the network. It knows the segments, it knows which labels to put in the label stack. It puts the label on the label stack and forwards the packet, right? So the top label there, 16,099, will get the packet to P3. But as normal in the MPLS world, we always do penultimate hop hopping at the last but one router. So the one router before the endpoint of a segment, penultimate hop hopping. So in the end, the packet arrives at P3 with only 2 labels. P3 looks at the top label and says, that's a label I assigned, 24,001. Again, penultimate hop hopping, removes the label, forwards the packet with the remaining label stack to P6. And then P6 just looks at the label value 60,007 and says, okay, I know this label, that's the label of P2, and every router along the last segment will forward the packet to P2. Okay. So what do you need to remember? It's all about labels. One segment is one MPLS label, and of course you need a link state routing protocol, ISIS or OSPF. There's one special thing, the local label block. That's something we didn't have years ago. Now we do it just in case you want to do something specific, like really assign statically an adjacency SID label to an interface with a fixed value. So if you reload the router, it remains the same label value. Or you have something like tree SID, tree multicast SID segment routing. So that's the solution where we have multicast for segment routing. You have a controller, etc. There you can use those labels as well. Most of the time you will not need it. But there are some show commands to verify that label rounds, typically 1,000 labels, that will be enough, so you can configure that. And typically, it will start at 15,000 up to 16,000. One thing, if you configure it, so you make a mistake, there's an overlap with the sRGB. So the segment routing global block, where we take all the prefixes from, then it will not work. There will be an issue, of course. But when you will have a syslog message, when you do the show commands, show segment routing, local block inconsistencies, you see that there is something wrong. However, the only way to fix it is to clear it. But of course, all the labels will be reprogrammed. They will be tied to different prefixes, services, and so on. So it will take a very short time, but all the labels will be reprogrammed, and it will have an impact on your services, of course. That's SR-MPLS. Although I have the feeling I'm missing one slide. Where was I topic? Oh, no, it's coming later, sorry. All right. No questions on SR-MPLS? Nothing burning? SRv6 and the later microSID, what is it? Well, with SRv6, we need IPv6. Guess what? So we're going to have an IPv6 header. We can't get around that. But we will also add an SR header, SRH, with extra information. What do we put in that extra information? All the segments. What is a segment in the SRv6 world? It's an IPv6 address, right? Or a part of it. But for now, let's say it's an IPv6 address. So the destination IP address, that will be the endpoint of a segment. But we have multiple segments. Where do we put them? We're going to put them in order, reverse order, but okay, in order in the SR header, SRH, which of course has a variable length because you can have multiple IPv6 addresses there. So how does it look like when we fill in the fields? The next header is just a routing header, so number 43. We are used to that. But now, in that field, the routing type, we have 4, and that's kind of the newer routing type. That's for segment routing. And then we know that what comes behind it is the SRH, the header. So what's important? Well, the segments, the IPv6 addresses. Reverse order, so bottom to top, 0 to whatever, n-1. We're engineers, we start counting at 0. The last segment is at the top. First segment will be at the bottom. And then important, the segment left is kind of a counter, or no, a pointer, sorry. A pointer to where we are currently, to the active segment, right? So if you sniff the packet on the wire, that pointer will point to the actual destination IPv6 address. Because that IPv6 address, which indicates one segment, will be also the destination IP address, all right? That's kind of great because when we are forwarding packets, the IPv6 header is already big enough. We just need to look at the destination IP address for the forwarding. We don't, at every hop, have to go and look into the SR header. In short, instead of MPLS labels, we put segments in the SRH. So that IPv6 address, it's pretty big, 128 bits. We can carve that up, and we have to. The first part, which is typically 40 bits, is the SID block. This is just a prefix, so /40 IPv6 prefix, which is common to all the routers in your network, right? But then you need to identify, of course, the router itself. So we have a node ID, which is different for every router. So together, 64 bits identifies a node in your network. You will have a prefix also, /64, which identifies a specific router in the SRv6 network. Then we have a function, and then we have an argument. Okay? The function, so the node ID. When we do a lookup of the destination IPv6 address, this is to get the packet to the endpoint of the segment, the router. We have so many bits left, we're also going to put a function. What does the function do? Well, simply said, when the packet gets to the node ID, the endpoint of the segment, the function will tell that router how to forward the packet, if it's there. Either, if it's not there, it will be just punted. But the function might say forward the packet this way or that way, over this interface, or do an IP lookup, or do a MAC lookup if it's EVPN, and so on. We are talking here about a complete IPv6 address that we are carving up in this way. We call that the format F1, the first one that we have, also commonly known as full SID. So this is the SID block with the node ID, /64. And then the function, 16 bits, is what I just explained, what the endpoint router at the end of the segment, how it will forward the packet further down. The argument, pretty rare. I think if you would see that, there's one example in the EVPN world, which happens to be the session that came before here, but only for bump traffic. But otherwise, it's not that common yet. So how does the forwarding work? I think with MPLS, everybody is familiar with that. The label stack, label popping, pushing a label, etc., etc. Everything is really well known. With SRv6, well, it's IPv6 forwarding, but with a header. How does that work? Well, the source node, because we have a link state protocol, knows the complete topology. So it knows the destination of the last hop router of the first segment, and then the rest of the segments will be filled here in the reverse order. All right. So every router now knows, okay, we need to forward the packet to this destination, which is router 1. If there happens to be a router, a transit router there, which does not understand SRv6, that's not a problem. It will just forward the packet based on an IP lookup of the destination IPv6 address. It's still a kind of a regular IPv6 prefix, which is advertised by router 1. So that will work. So not necessarily all your routers need to be SRv6 capable. But once we hit router 1, that router will say, okay, that's my IP address, right? It will move the active pointer SL1 up 1, and that new address that you see here, that will become the new destination IPv6 address. The packet is forwarded. R2 will do the same. The last segment, that becomes the new destination IPv6 address. Right. At this point, the SRH doesn't really make a lot of use anymore, and it could be removed. It doesn't have to be, but it could be. On our routers, it will be, right? And we call that penultimate segment popping. We are popping the SRH. We're not popping the segment. Again, something similar from the MPLS world. Okay. So this is how the forwarding works with SRv6. We just go up the ladder, and each time, at the end of a segment, pick a new destination IPv6 address. Comes in microSID. Also known compressed SID. We're going to carve up the IPv6 address even more. And actually, instead of one segment, maybe two, put up to 6 segments in the IPv6 header. Okay? So first you have a part which is the prefix, and then 16 bits, so 4 characters, will be each time identifying a node or a function. A node, get the packet to the router. A function, from the endpoint of the router, or the endpoint of the segment, how does the router forward the packet? Okay. So first of all, the block. It's now only 32 bits, not 40 anymore, so a little bit less. But every router in the SRv6 microSID network needs to have this prefix configured. And then we have the specific microsits, router 1, 2, 3, 4, each time 16 bits. The rest, if there are less than 6 microsits, we just fill it up with all zeros. So the IPv6 header could look something like this. We just have a destination IP address, and the multiple endpoints of the segments are encoded here, each time with 16 bits. So an SRH is not necessary here. In some cases, it might be needed. For example, if you have more than 6 microsits, well, there's no more room, right? So then you can add an SRH, but it's not a must. So active SID is always at the left, and then we have the other SIDs. Because what will happen in the forwarding, each router will look at the prefix, so the SID block, and then the next 16 bits, and make a forwarding decision on that. In this case, forward it to router 1. Once we hit router 1, we just remove that part, the 16 bits, bit shift 16 bits to the left, and forward onwards. Bit shifting is something the routers can do, of course, very quickly. So let's have a look. The head-end router, the source, creates a packet, the block, and then multiple SIDs. The first one is the active SID. So the routers, up to router 1, they look at the prefix and the first 16 bits, so the active SID. And then everybody knows how to forward the packet to router 1. Even if there's a router in there which doesn't understand microSID or SRv6, it will still be forwarded to router 1. Because the block, the 32 bits plus the 16 bits, together is always advertised by every router as a separate prefix, right? In the old fashion, not by new TLVs in the ISIS or OSPF protocol. Once we get to router 1, we remove the first 4 characters, so the first 16 bits, and bit shift everything to the left, 16 bits, and now it will be forwarded according to the prefix and the active microSID with a value of 2. So everybody knows that the packet needs to be forwarded to router 2. And it continues like this, so at every endpoint of a segment, we bit shift 16 bits to the left until we hit the destination. So now, microsits, we are carving up the IPv6 address. What you need to know, there's like a, right, of the 16 bits. We have a part, what we call the global identifier first for the microsits, a big value. And then starting at 0xe in hexadecimal becomes the special functions. Okay. So what you need to know is that the first part is what you can configure, and this will identify the node itself. So this is what you configure on every router, 1, 2, 3, 4, 5, etc. 0xe is reserved. That will be the special function, the forwarding function, that every router will dynamically assign. For example, forward out of this interface, forward by doing an L2 lookup or an L3 lookup or a cross connect, whatever. But the router will assign that. We will see it with show commands. Yeah. Important is in the microSID world, whatever identifies a node, we call that UN, micro node. Whatever identifies the adjacency SID, so pointing to an interface, we call that the UA, micro adjacency. That's an example of a global SID. It's just regular number, but anything starting with E whatever will be a local uSID. It will be automatically assigned by the router. All right, a bit of configuration. This is how you configure it on iOS XR. Segment routing SRv6, pretty simple. Locator, that's what identifies the router in the network, right? So it needs to be unique for every router. You can see there at the prefix part, we have the block part, and the part in blue, 101, that's the identifier of the node ID. together, those two parts together, /48, is the prefix that the router will advertise. Okay. That would be full SID. If you want micro SID, you have to configure micro segment, behavior, whatever. Okay. If you're wondering what PSP is, it's the penultimate segment popping, but that's the default what we do. And USD is the ultimate segment decapsulation. So, for example, when you forward an IPv4 packet over an SRv6 packet, of course, in the SRv6 world, you have to put a new IPv6 header on top of the IPv4 packet, right? And then at the egress PE, you have to remove the outer IPv6 header. That's encapsulation, ingress PE, decapsulation, egress PE. That's what USD stands for, ultimate segment decapsulation. We will always do that. The egress PE will always decapsulate. So there's no choice there, you have to configure this. Just to wrap it up here, two parts, SRv6 and uSID. And let's have a look at the two forwarding possibilities. There are many, but we will just have a look at two. On the left-hand side, we have full SID. So when you look at the header, there you see a list of IPv6 addresses, well, bottom to top. The destination IP address will be the active segment. So when we reach to the endpoint of a segment, router B, he will just move the pointer and replace the destination IP address from B to C. That's it. In a microSID world, what we have just explained, we don't have an SRH, no header. We will just bit shift 16 bits to the left. So we remove the B part, it becomes just C. Yeah. So just bit shifting. Another example is the XConnect. XConnect, I think you're familiar with that in the pseudowire world, VPLS, VPWS, EVPN, and so on. We don't really do a lookup. We get a packet, we look at the label or SRv6 header, we just forward it out on a specific interface. The forwarding is embedded in what we got, for example, the MPLS label. So on the left-hand side, SRv6, again, we have the SRH header there. It's not just a simple node that's there. We have a node, but we also have the function BC, meaning get the packet to router B. Once we're at BC, forward the packet on the link BC. So when the packet hits router B will move the pointer, and now the new destination IPv6 address will be router E, the next one in the SRH. Microsid, it's going to be bit shifting again. We have here 16 bits for router B, and then 16 bits for the function forwarding from B to C, so BC. Well, we're just going to bit shift in this example 2 times 16 bits to the left. So remaining is E here, which will be the only microSID left in the destination IPv6 address. Any questions on this? Functions and behavior, a couple of great commands is just show segment routing SRv6. You see the full SIDs at the top and the microSIDs at the bottom. So you would have to look, and after a while you will become familiar with that. What are the end functions? Like you see here for node 3, you have an end function. And then probably for every interface, you have an end.x function, adjacency, SID, and so on. And for microSID, you have something similar, but it will be identified by UN or UA. Okay. That's just the local SIDs on the router. So after configuring, this might be the first thing that you want to check on the router. The order is a little bit wrong, but we'll survive. Okay, so bringing up segment routing with SR-MPLS. Configuration-wise, so back to MPLS, it's just a simple command under ISIS or OSPF, very simple. In the end, you do want to verify that MPLS is enabled on the interfaces. Even though you might not have LDP, it's removed, or classic traffic engineering. With segment routing, MPLS will be enabled on the interfaces. Okay, so that's something to verify. Configuration is pretty simple. If you're running ISIS, you do want to check the ISIS database. So one of the most common issues when we are looking at issues with segment routing is the topology, and you knowing the topology, right? Be it basic SR and SR forwarding, or more complex SR policy, or working with a controller, or doing 3-SID multicast, it's many, many times an issue with the topology. So that's something important, something to look at. If you look at the ISIS database in detail, and you look at one LSP, a link state packet, the header, okay, that's what we've had for almost 30 years now, so that's known. But then you will see some new parts which are related to segment routing. Right? SRB with a range, 8,000 labels, some flags. We're not going to go into detail, but the flags can say it's for IPv4 only, or also IPv6. Can you use the link for a backup, so for protection and so on. Right? In short, you must have one prefix SID per router, and then X number of adjacency SIDs, one per interface. So this is the sRGB, the global block, and then adjacency SIDs, one per interface. In the end, the adjacency SIDs are always advertised in a relative way as a number, not as an absolute value, so not as an MPLS value. But you can configure it either way. So relative value, 5, index 5 is from the starting point 60,000 plus 5, or as an absolute value, so an MPLS label. OSPF database, guess what? What we use here are the opaque LSAs. Opaque LSA type 10 is where we carry all the information for segment routing. And then you have specific LSAs in opaque type 1, type 4, 7, and so on, where we put the sRGB range, the adjacency SIDs, and so on. So the same information, of course, as ISIS, but in different LSAs. It's a little bit more fragmented. It's a link state protocol. All of this information is advertised to every router throughout the network. Topology, like I mentioned, is very important. With ISIS, there's a nice command, show ISIS topology. From the router where you are at, it will figure out the topology to every other router in your network, right? So you must have that. You can look at it in detail, and then you will see some extra segment routing information like the sRGB, etc. Of course, you need to use metric style wild for ISIS. You might have the local block there, SRLB as well, and so on and so on. Again, checking the topology. There is a nice command, show ISIS route SR only, and you will see only the SR routes. What does that mean? It will show you all the prefixes of every router in your network. So any router you have, you connect to it, you do this command, you should see all the prefixes of all the routers, right? Only the labeled ones, only the labeled prefixes. If you have prefixes on links, that will not be labeled by segment routing by default. We don't do that. We only do the loopback/32s. And if you do the detail command, you see even more details, like some of the flags used for protection, and so on. Is this as a This is in different order than the slide you have downloaded. I'm sorry for that. This one is hidden anyway. Let's skip this one. Okay, so what I wanted to say a long time ago, in SR-MPLS, all the forwarding is as you know it from classical MPLS, be it based on LDP or RSVT, right? There's nothing new. Label popping, pushing, swapping, experimental bits for quality of service, the TTL propagation, everything is as we know it. And that's of course great because then we don't need to change any of the hardware, the ASICs. If you can do MPLS forwarding with LDP traffic or classic traffic engineering, we can do it with segment routing. Okay. The output is just MPLS forwarding as we are used to. So if you do show MPLS forwarding, the LFIP, it's everything that we are used to, except the part that doesn't matter for the router, but matters for us when we are troubleshooting. So you see here the prefix SID, the JCC SID, maybe a binding SID, so the label attached to the SR policy at the head end router and so on. That's different, but the router doesn't use this for forwarding, right? It uses everything else for forwarding. So data plane, SR-MPLS, nothing special, nothing new. Some possible issues when you're deploying SR-MPLS. You know that when you go from the LDP world to the SR world, you can actually run both of them together. Only one should be active. By default, it's the LDP because it's the oldest one. There is a command under ISIS OSPF, SR prefer, and then when you configure this, you switch over to the forwarding based on SR MPLS labels. So that's something to watch out for. Most of the time, there are config mistakes or mistakes specifically to the prefix SIDs, and so on and so on. And a lot of the time, those basic issues can be figured out by looking at ISIS OSPF and the topology, the database, and so on. The good thing is, in this MPLS world, that it's still all working. So if you do a ping, a trace route, and so on, it still works, and you even have labels in the output there. Very nice command, not specific to SR-MPLS, but it can be used for SR-MPLS, is a trace route with nil-FAC. Nil-FAC means we don't care about the context of this FAC, we just put FACs. One FAC is one label. So we can do a trace route from R1 to R7 on any kind of path, as long as you specify that path. What is a path in SR-MPLS? It's a number of segments. What is a segment? An MPLS label. So what do? You just identify some segments. It could be the segment to R6, then the JCC SID to R4, and then the segment to R7, which is a prefix SID. So we do a trace route, MPLS nil-FAC, we specify the three labels, the three segments, I shoot the packet off. And the packet will follow exactly that path, so the non-shortest path. Right? And this is important when you're doing SR-MPLS, because there might be a high chance that you're also doing policy routing, right? Source routing. So you can verify all the paths in your network, not necessarily the shortest path. Great command. So sorry about the reordering, but now back to SRv6, microSID. The configuration, kind of simple, segment routing, something under ISIS or OSPF with a locator. Why do you need to name the locator? Because we can have multiple ones. If you just have one topology, you just have one. But if you have multiple topologies, flex-algo, flexible algorithm, that's what we call it, then you will have to configure different locators, one locator per topology. Okay. It's SRv6, so we need address family IPv6 under OSPF or ISIS. And finally, what is important is the prefix there. Remember the block, FCBBBB0, and then the node ID 101. Okay? And we do advise you to use the ULA, so the unique local prefix range for IPv6, which is FCBB, or FC/8 actually. And then finally, microsegment behavior, that just enables microsegment. Only one extra command for microsegment. Micro-SIDS, micro-SR, or compressed SIDS. Okay. Verification, again, the topology is very important. So you're going to dive into the ISIS database or the OSPF database and verify what you have there. Again, you have one prefix SID per router, which is attached to the loopback prefix. Again, in the SRv6 world, it will be identified by UN, as you see here. And then per interface, at least, you will have one UA, an adjacency, microSID adjacency. You can see the format, F3216, so 32 bits for the block length, 16 bits for the node ID. Together, 48 bits. That's what you need to verify per router. Some commands already mentioned, show segment routing SRv6. What do you have locally, and then deroutes. Ping trace route still works. So IPv6, you can still do a trace route. It's just IPv6, so you will see IPv6 addresses. Pretty simple. Okay. As we will see in the next few slides, there will be a SID advertised by BGP when you are using BGP for whatever service you are running. A service being L3 VPN, it uses BGP. L2 VPN might use BGP, some cases. EVPN for sure will use BGP. In those cases, BGP can advertise a SID as well. Why is that needed? Well, think about the MPLS world. You were running L3 VPN, for example. You were running BGP. You have a next hop, which is the egress PE, but you have a label associated with the VPN v4, VPN v6 prefixes. We don't have labels here. So what do we use? Well, we're going to use, guess what? Something SRv6, an IPv6 address. So you see here, for the SIDs, attached to BGP prefixes, SIDs. Right? And that's what the ingress PE will use to attach to the packet when we are forwarding the packet. So instead of putting labels on top of the packet when we are forwarding the packets, in the SRv6 world, the ingress PE who does the encapsulation will put an IPv6 header with one or more IPv6 addresses there, in the SRH or as microsids. Right? So now BGP also need to carry those SIDs. So, in the overlay network, let's say we are doing L3 VPN. We have BGP between PE routers. What is important? Well, the prefixes we advertise. In this case, VPN v4. The next hop is PE2, egress PE. That's fine, but we cannot put a label there, right? It's not MPLS world anymore. So what we put there instead of the MPLS label is the SID from PE2, this part to get the packet to PE2, and then the function. Once the packet gets to PE2, how to forward the packet to CE2. In short, how to forward the packet could be a couple of things. Typically in this world, L3 VPN, it's three things. If you remember, allocation of labels, it can be per VRF, per prefix, or per CE. It's the same thing here. If it's per CE label allocation, the PE router doesn't do an IP lookup, it just forwards the packet. If it's per VRF allocation, in the old world label allocation, the PE router will have to do a lookup, IPv4 or IPv6 in the VRF routing tail. Packet forwarding, we have an IPv4 packet. We encapsulate with what? With an IPv6 header. So we have a source and destination IPv6 header. What is important in the destination IPv6 header? We have two parts. The first part, the block, but also the node ID of PE2. and then the function. Once the packet gets to PE2, how to forward it to CE2. So what needs to be happening here is that BGP needs to advertise SIDs. That's the new part here. Configuration-wise, under BGP, under the VRF, you just tell the router for that VRF, start doing SRv6 now. And you do that by configuring a locator. And you can say do per CE, per VRF, per prefix allocation, as we are used to in the MPLS world. Okay. And then BGP, you can verify with show BGP, VRF, whatever, local SIDs, what the local SIDs are that you have on the Ingress and the egress PE. And of course, that will be advertised to the other PEs, right? And typically, the behavior can be, like you see here, microSID DT means lookup in the table, T is table. So do an IPv4 lookup. That's per VRF label allocation, not label. DX4, that means do a cross-connect lookup for IPv4. So you don't do an IP lookup, you just forward the packet out. That's typically per CE label allocation. So new functionality for BGP, it needs to carry quite a bit of extra information for SRv6. Namely, what will be attached to the VPN-v4 prefix, some information that comes from the remote PE. Namely, the format, F3216 here, microSID. The SID, so the block and the node ID, egress PE. And this is a bit peculiar, the function will be 16 bits instead of the 20 bits of the old MPLS label. So of course we don't have an MPLS label here, but instead we put the 16 bits of the function of the remote PE router. Right? So this is XConnect or IP lookup at the remote PE router. And finally, the behavior, there's a number that's a bit cumbersome. You will have to look it up at a table. So you go to the IANIA website and you look up what that number means. It's typically going to be an IP lookup or a cross-connect lookup and so on. In this case, it's an endpoint behavior. And the next compressed SID is DT4, so IPv4 lookup. There's a table here for your convenience. These are the ones that we use the most, so number 63 is there. Finally, this prefix on the Ingress PE will be installed into the FIP, into the CEF table. And this is what it will look like. Of course, the next hop is the IPv6 address of the remote PE, remember PE2. And this is what we will actually put on top of the packet, right? The block, the node ID of the remote PE, and then the function, how the remote PE should forward the packet. The last line is what goes on top of the packet. Next example, not L3 VPN, quite new, is eVPN. eVPN is quite complex, I think you might know that. And it relies on BGP heavily. It has a lot of route types, 1, 2, 3, 4, 5, up to 12, I think, now. The first 5 are the most important ones. Now here, just an example, just for route type 1. This is kind of the auto-discovery. I'm a PE router, and I want to do eVPN for this ESI. ESI is an Ethernet segment. So think of a VLAN or a link, right? So when you configure eVPN, and that's fine, that's a service. BGP will do the signaling end-to-end. But now in the core, we don't have MPLS. We have SRv6. So that's quite different. So now what BGP needs to advertise is, of course, the prefix. In this case, it's a route type 1 for eVPN, doesn't matter. But attached to that, again, we will have this SID. Okay? identifying the egress PE, and the function how to forward the packet, the last 16 bits, from the egress PE to whatever is next, the switch or router, the CE router. When we look at the prefix, or first the packet forwarding, so with EVPN, of course, we have layer 2 traffic, right? A layer 2 frame comes in, we add an IPv6 header. On top of that, important is the destination IP address. Again, identifying egress PE, PE2, and then once the packet comes in at PE2, how to forward it. This is the E05. Remember, global microSID 0 to 0x, but starting from 0x, this will be assigned automatically from the router. It's a function. Of course, decapsulated, and the frame gets forwarded to C2. So in the end, this is how it works, and it works similar for all the overlays services, be it 6PE, 6VPN, VPN v4, VPN v6, and so on. Configuration, we have router BGP, address family again, for L2VPN, EVPN. But now under EVPN, you have to tell it, hey, use in the core not MPLS, but SRv6. So again, you would have to configure this locator. Okay. Now, when looking at EVPN with the specific EVPN commands, show EVPN, EVI, and so on, you will see SID information, the local SIDs, the remote SIDs that the router learned, and so on. Again, this is what the SIDs is what will be put on top of the packets, the frames, when forwarding the frames through the SRv6 network. Again, more into detail, some things are attached to the BGP prefix. We have the SIDs there, the format, 3216. And again, a number for the behavior. Now it's 65. 65 is DX2. So cross-connect. Don't do an IP lookup. Just forward the frame out of the router on a specific interface. And again, the label value, that's not a real label. We don't have MPLS here. That's the function, right? How to forward a packet out of the egress PE. Kind of an overlooked tool is a traceroute command with SRv6 carrier. What is it? Well, we have seen the traceroute for IPv6. With this command, you can do traceroute with carrier. And carrier is just a waypoint, an intermediate destination, like you have on the car navigation. And you can put multiple IPv6 addresses there. So this traceroute will go to the endpoint, but via this one. So that's one segment. If you put 2, 3, 4 IPv6 addresses here, you have 1, 2, 3, 4 segments. So again, a way to verify the path through your network by a traceroute command. And it will tell you SL, segments left, and so on. But it's a traceroute. Any questions on SRv6? All right. Ti-LFA. So Ti-LFA is topology independent LFA. LFA has been around many, many years. It relied on nothing specific, just some calculation inside the router. Then came remote LFA, which relied on using a targeted LDP session from one router to the other. We call that remote LFA. Finally, topology-independent LFA relies on segment routing. So for Ti-LFA, you need segment routing. It's called topology-independent because no matter how complex your topology is, you always have protection. This was not the case with LFA. This was simple calculation. Between 50 and 90% of the times you had protection, but not always. Kind of depended on the complexity of the network, meaning how much meshed it is, or if the metric on the links are similar, 10, 20, 30, that's okay. But if it's 1 and 1,000 on another link, it's going to be difficult to find a backup path or protection. But Ti-LFA is LFA when you have segment routing in a network. It's pretty simple. Again, under ISIS or SPF, you already have LFA enabled. That's one command. There's an extra command to enable it for Ti-LFA. That's it. No extra signaling. It's just extra calculation on the router who does the calculation for finding a backup path or protection. And this LFA is also called fast reroute, by the way, FRR. What do you need to verify it? Well, there are two things. When you configure it, the router will start calculating backup paths. So you need to verify, do you have a backup path, and is it correct? Then you can actually test it, but you have to pull a link and see how fast it reroutes, right? And it's a bit more complex. You have to measure the traffic loss, you have to look at traces on the router, what happened, etc. But the most important part is, before the failure, checking if you have a backup path or not, right? So you have a primary path, which is protected by a backup path. In this case, in this example, we have a link here, which is protected by a backup path. Now, you can have a very simple example, which is typically a triangle, where the backup path is just 2 hops, right? Protecting the primary path. You can have a square, which is a bit more difficult. That backup path will be protected by 1 segment, whereas the triangle was 0 segment. So you don't add anything on the backup path. With 1 single segment protection, you add 1 segment. In this case, which is the most difficult one, it's double segment. It's 2 segments. Why? Because the network is a little bit complex. Why is it complex? You can see this is not a triangle. This is, many hops to go back to the same destination as the primary path. Not only that, but every link in the network has a metric 1. It's correct on your slides. Whereas here, it's metric 100. So suddenly you have a big hill to cross, right? For that, you need an extra segment. And you will see that. You only need 3 commands: show route, something from the protocol ISIS or OSPF. You look at the RIP of the protocol, in this case ISIS, so it's show ISIS IPv6 fast reroute. And then finally show CEF, the FIP information. And you can see in this case, indeed, we have double segment protection. The first segment goes to P5, and then we need another one to cross this link with a high metric. The first segment is just to get the packet to P5, prefix it, just get it to that node. Then we need something special. We really need to make sure we cross this link. We cannot say just go to P6. No, you need to cross this link over this adjacency. So to get to P5, we're going to use a prefix it. But in the world of LFA, we call that P node. It's just a name. It comes from mathematics. Then to cross from P5 to P6, we have to cross a link. We're going to use an adjacency SID for that. So that's what we call Q node in the LFA world. Okay. And you remember, prefix SID, adjacency SID, they either have a full IPv6 address or something from the microSID world. So finally, when you look at CEF, you will see that this is what we push as destination IPv6 address in the IPv6 header. And even though it's double segment, I would have expected 2 IPv6 addresses, but in reality it's just 1, because here you have the 2 segments. This one is to get to router 5, and then the 541 is the adjacency SID from P5 to P6. Right? So both P and Q are present together in the SID that we put on top of the packet when the protection kicks in, of course. So the primary link needs to fail, that's obvious. When you do a packet capture, you will see that what we have just seen on the previous slide is there as the destination IPv6 address. We do have an SR header, right? And why is that? Well, guess what? The original destination, previous picture, was router 7. So we need to put somewhere the original destination IP address. So that will be there. But there's not much else added. It's just, yeah, SRH with one IPv6 address. This slide was changed, so I'll skip it. With microSID, it's very simple, but instead of full IPv6 addresses, you have the microSID entries there. But it's exactly the same thing, the same example for a double segment calculation. I will skip those slides. Okay. And the packet capture is exactly the same. The only thing you need to remember here is the middle part. When you look at protection, you kind of need to know from the old LFA what is a P node and a Q node. You can look it up, you can Google it, you will find some information. But when we look at the SRv6 or microSID world, we see that a P node is really a UN, so prefix SID or microSID. And a Q node is a JCC SID or UA. That's what you need to know, because that's what you will see in the output from the show ISIS or show SEF commands. Okay. SR policy. Any questions on protection? Nope. SR policy, what is an SR policy? Well, we want to do, finally, traffic engineering or source routing. And a policy is something that you configure, and it's made up of three things, really. The head end, obviously, where you configure it. The tail end, or the end point, you configure that, and the color. The color is very important. It's everything in the SR world. And the color is also something that will be attached to the service prefixes. We will see that. Okay. So with the policy, it's just, replacing classic traffic engineering. You want to do source routing through the network, either with MPLS or SRv6. The mapping of traffic onto the SR policy is most of the time automatic. So if the router is receiving traffic following a certain prefix, it will use the SR policy, and it will be forwarded out into the MPLS or SRv6 network. Configuration, kind of simple, segment routing, and then two ways to do the policy. Second part here is dynamic. So the router itself calculates the path through the network, each time with X number of segments. It's possible that there would be a controller somewhere helping the routers to do the calculation, right? But normally the head-end router can do it by himself. Or you put something static explicitly, as you have here, the same like in the old RSVP classic TE world, where you just put every next hop, right? And each time you have a hop, it's a segment. So in this case, kind of 4 segments. You can put it by an adjacency, an IP address, or by label. One thing which is, well, something you need to know is the name of the policy that you will use in the show and debug commands is generated by the router. So you find first you need to do show segment routing traffic engineering policy. You will see a summary of all the policies. You have to pick your policy. It's a combination of the endpoint and the color. You can guess it. It's always the same kind of syntax, but it's SITE_C color number, and then EP endpoint, whatever. And you will see there if it's up or not, which labels it is using, and so on. Again, a most common issue is the topology. My policy doesn't come up. That's what we always come across. Most of the time, it's a problem with the topology, and a lot of the time, it is a problem with the configuration, right? You missed something, or something got forgotten, whatever. And hence, you need to verify the topology. So again, you will look into, this time, not the ISIS or OSPF topology, but we show segment routing, traffic engineering. You see the topology. Yes, it's still advertised by ISIS or OSPF, but which is used by the traffic engineering. That's just more, that's a lot more than the normal ISIS or OSPF topology. You have a lot of characteristics, attributes which pertain to traffic engineering. For example, the different kind of metrics. You have IGP, TE, minimum delay metric, and so on. That's only for traffic engineering. It has nothing to do with normal IP routing. Again, what you need to verify is that you have the prefix SID and the adjacency SIDs there. The traffic from policy to the traffic mapped to the policy, that will be automatic. How does it work? Well, there's always a caller, as I said, caller 2000, for example. Guess what? The prefix, service prefixes, in this case VPN v4, there will be an extended community, well, they should be attached to it, and that will hold a caller. That's something that you configure on the remote side, the egress side, the egress PE side. You attach whatever caller to every set of prefixes. For example, one caller per customer. On the ingress side, we pick that up by looking at the BGP route, and we see the external community. We see the caller. We match the endpoint, 10002 here, and then we know, okay, traffic for this prefix will go onto that policy with the caller 2000. No need for static routes or anything like that. Okay. And then we show segment routing, traffic engineering policy. You see that it's actually mapped, and the policy is up with a specific path. Typically, what will go wrong here is that either the color matching didn't work for whatever reason, maybe BGP didn't carry it, or the second part, probably the most important part, with the SR policy, the router, the head-end router, needs to find a path through the network, of course, right? If that doesn't work, your policy will be down. In the end, show Ceph, again, you see there the service prefix maps to a next hop, which is actually a policy. So now we know, if you look at the labels, when forwarding traffic, so for example, you do a trace route in the VRF, that we use those labels of the policy. So the policy is working. Good tip for troubleshooting, you can put a static route and you can actually put it to the policy if you figured out the policy name, and then you can start pinging, trace routing, whatever, according to the static route, and see if that policy is working before putting live traffic onto it. So before coloring the BGP routes. When a policy is not functional, typical issues are, it's down because it didn't find the path, something is wrong with the SID, you have two routers with overlapping prefix SIDs, and so on and so on. You can read it here, it's a bit of homework. Same kind of things, but this time it's for SRv6. So we have a policy with SRv6, it's down for whatever reason. One thing you should note is that when you do the show segment routing traffic engineering forwarding command, so with forwarding, you see a counter there. All right, so think, is that counter increasing or not? If it's not increasing, your policy is not working, of course. So some possible data plane issues, packets getting dropped, the packet is not taking the desired path, and so on. So many issues with possible solutions there. Again, the first thing you should check is the database, the topology, and the configuration, of course. In iOS XR, we have traces for almost everything. So we have traces for segment routing as well. So working or not working, if you look at the traces which show segment routing, traffic engineering trace, you can find a lot of information back. Now those traces are pretty chatty, they're pretty big, but I give you an example where the calculation of the path doesn't work, and it will usually give you an indication as to why. Or if it does work, it will tell you, I found one, this is the metric I'm using, this is the labels that I'm using, the segments, and so on. So you can check the traces if something goes wrong. Logging, that's not enabled for SR policy automatically, but you just configure logging under SR policy. And if the policies go down or up, or something is changed with the candidate path, so you might have one policy but with multiple candidate paths. For example, one is dynamic, the other one is static, etc. It will tell you if you're going between them. And I gave you a table here with some possible logging messages, some errors. Okay, the policy will go down, but also some warning and some notices. Verify the policy. Again, it's ping and trace route. Once you have a policy, you can ping SR-MPLS and trace route MPLS and verify the whole policy, the whole path, all the segments. But for this, you must have MPLS OEM enabled on every router, which is not by default on iOS XR. It is by default on iOS XE. ECMP, really good. A lot of the problems occur when the customer calls in, opens a case and says, sometimes it doesn't work. Those are, of course, the most difficult issues to work upon. And sometimes means it kind of depends on what traffic, which customer is sending what traffic. Well, a lot of the times it is because of ECMP. Right? And with this ping, or also trace route command, SR-MPLS, you can put a fake destination IP address. That destination IP address is not used. We use the MPLS for the forwarding. But routers in the middle who do ECMP load balancing, they might look at the destination, maybe also the source IP address, for the load balancing algorithm, right? And typically, if you put a range of 16 IP addresses there, we will hit all the different cases of load balancing on an intermediate router somewhere in your network. And then you can figure out if it's working or not, or in this case, for example, it might not be working for one specific destination IP address, for one bucket in the load balancing algorithm. Finally, show segment routing, traffic engineering with forwarding. I mentioned it already. There are some counters there in the middle and at the bottom to see if the policy is really forwarding traffic or not. SRv6 policy, it's kind of similar to the SR-MPLS policy. You just put a static or an explicit path or dynamic, but it's all with IPv6 addresses, with or without microSID. So it's kind of straightforward as well. What's next? You might have a router with issues. You could be running out of resources. You can check that with show controller NPU resources. We have different kind of boxes, so it could be anything going on there. Some of the routers, NCS 540, 5500, they need a hardware module profile command to make it work for microSID. Otherwise, nothing will work. Pretty obvious, but okay. And finally, show segment routing. SRv6 Manager gives you a great overview. It's pretty long, but a great overview of what the box is capable of. How many SIDs, microSID or not, what are the kind of functions it supports, and so on. Typically, when looking at the SRv6 world, yeah, it's kind of similar as with SR-MPLS. You might have programming errors, the TCAMs are full, you're dropping traffic. So you would have to figure out what is happening where. For example, a stale entry, yeah. If it doesn't change, try changing things and see if the FIP or CEF entry changes or not, or the LFIP entry. If you have traffic drops, guess what? There are commands for that. The one command to rule them all on iOS XR is show drops, right? Or show drops ongoing. That's a great one. And as I mentioned, show segment routing SRv6 Manager is a great one. It shows you the parameters, the capabilities that the routers support, which formats, F3216, F1, what are the label ranges, or how is the carving up of the IPv6 address is done, and so on. Is the box out of resources? OR, TCAMs are full. And finally, the forwarding capabilities, the endpoint behaviors, cross-connect, IP lookup, IPv6 lookup, etc., etc. And that's the final one for that output. And how many locators? Typically 8 or 16, one locator per flexible algorithm per topology you have. Okay. Any questions? First 5 rows? Nobody? Troubleshooting examples. These are examples from the last year I've seen, worked upon. So they're real cases that were opened from you, the customer, and worked upon by the tech. So first of all, a helping hand. I mentioned the topology is very, very important, right? And you need to check the topology. Here's one possibility that might help you. There is something which is called graph visualization. In the end, when you have the ISIS or OSPF database just from one router, you can make a graph out of that. Just one step, ISIS, OSPF, 2 steps. How to do that? Well, you need a tool there, WebGraphis. You need the dot file, which comes out of the router. So in this example, I had a CML topology. It's virtual, but it is a topology. And then it creates that topology. You might say, well, that's 10 times worse than this. Maybe yes. But I can quickly verify between a pair of routers each time I have connectivity in both directions. There are each time 2 lines. It's graphs. So that's the procedure. What you need to do is, in ISIS, you just do show ISIS database graph for both. And that's the command that people don't know. That gives you the dot file. You put it on that website, or you create a script, or you download a Python script somewhere, and it will give you the graph. Pretty simple and effective. If it is OSPF, you do need an intermediate step. You need to download the router LSA output, all of them. Run it through that script online there, and then you have the dot file and you put it on the previous link. And you have a graphical visualization. Or something else which we provide, you pay for, which is Crossworks. And part of that is CNC. That's really a great tool. Does visualization, not only of what you have configured, but of course, all the live states of the network. So all the policies, SRv6 or SR-MPLS are there, the traffic forwarding, there's logging, there's alarms, everything you can think of. You can play with the metrics to see what's going to happen if you change something, etc., etc. Right? So that's CNC, part of Crosswork. Again, it will help you to look at the topology. Customer opens the tag case, he says, nothing works. Okay, let's have a look. Show segment routing, traffic engineering policy, the policy is down, but actually the forwarding was working. We were using MPLS forwarding, it actually worked, and so on. But okay, the policy is down. We have figured that out. But right, none of the policies were working. What was the problem? And this is, strangely enough, something that happens from time to time. It's already there in a rectangle. We see a LAN adjacency. What is the problem? Segment routing, ISIS, OSPF will only work if the links are point-to-point. We don't support broadcast media, and that's why the SR policy is down. So as soon as you put point-to-point everywhere on all the links on your network, the policies will come up and everything will work. Seems pretty simple, but it takes a while to figure out which link is misconfigured. Number 3, sometimes there's no ECMP over SR policy and native MPLS. This was also a problem in the past with native path and classic tunnel. We kind of have something similar now with SR policy and native path, so no policy, just MPLS or IP forwarding. On the left-hand side, we see a prefix, 2 paths, BGP multipath is enabled, great. When we look at the routing table, they're both A. It's working. Customer says, look, on this router I have, it is working, but I also have another router, very similar, same configuration, and it's not working. I have the 2 paths, native 1S policy, but by the way, they're not marked as multipath in BGP, and hence I only install the best BGP path in the routing table and use for forwarding. It's the same software version, it's the same configuration. Well, it turned out that we made BGP aware of this multipath between SR policy and native path. And some platforms, like on the left, do that and support it, and it works. And on the right-hand side is another platform which doesn't support it. Right? Something you need to know, but with this command you can figure it out, and BGP will tell you, I will do this or not, depending on what the platform is. We had some cases on this in the last year. Another example, autoroute. You might know autoroute from the classic RCP-TE world, where you have tunnels, and then autoroute attracts the traffic from any of the prefixes onto the tunnel, onto the SR policy. Right? So you expect when you configure autoroute for an SR policy that the prefixes will be forwarded onto that. There's only one, there's a big check, namely the next hop of the prefix needs to be the same as the endpoint of the SR policy. Customer says it doesn't work. Even though the configuration is there, I have a route, but it's not pointing to the SR policy. So what is wrong here? Well, it's not working because that route, it takes some time to figure out, of course, is an inter-area route and not intra-area route. Your policy, even though it might come up because maybe you have inter-area routing, you do have a controller, so the routers might know with BGP-LS and so on, your routers might know the topology of the whole network, it might still not work, right? Even though the policy might be up. And the reason is, autoroute, I always say autoroute announce, but that's classic T. Autoroute will only work if the tunnel ends inside the same area as the head end, right? So there's only one solution here, that it needs to be an intra-area route and not inter-area route. And then for those service prefixes, it will point indeed to the SRTE, to the SR policy. You must know this. Example 5, customer does something, comes back and says, my targeted LDP session goes down, so my pseudo wires are down. So in many cases, the pseudo wires are built up by targeted LDP session. That's what we started off with more than 20 years ago. Well, let's have a look. Turns out that indeed some targeted LDP sessions goes down, but when we look at the pseudo wires, they're not impacted. The pseudo wires are still there. That's kind of weird. So what happened there? And this took a while to figure out. We see that when we look at the protection, show as fast reroute and so on, that the protection is there, but it's done by Ti-LFA. Okay, we talk to the customer. That's kind of weird. You have segment routing, yes, but we're not using it. We're using just normal MPLS and LDP for the forwarding. So you don't have SR-MPLS prefer command? No, we don't have that. Okay. But they did do something, and we look at the last commit. They enabled fast reroute to Ti-LFA. So it enabled Ti-LFA. I would think as well, if you do that, it's not going to work because we are not using SR for forwarding. Well, it turns out, even if SR is not enabled for forwarding, we're still going to use Ti-LFA. Okay. Now, customer had remote LFA before. Remote LFA uses LDP, uses targeted LDP session. So now Ti-LFA kicks in and kicks out remote LFA and brings down the targeted LDP session. All right. Something that took a while to figure out, of course. But in the end, no harm was done. The pseudo wires were up. Okay. Next one, which is a bit router specific, you get some errors, failure, FIP failures left and right. If you look very, very carefully, but here it's in blue, you will already figure out what the, well, you might have a hint what the issue is, but it's not that obvious. In the end, we start looking at, okay, what prefix failed? Let's have a look at the prefix. We start looking at the prefix. Show SRv unresolved. Yeah, it's one of the unresolved, meaning it doesn't resolve down, it doesn't find the outgoing interface. It's not valid. Why? We look at the prefix, we look at the, we see next hop, we look at that next hop, sorry. We see that it's a labeled unicast route, BGP-LU, and then it points again to a policy. Right? But when we look in the, and we have autorouter announced for that. But when we do the show SRv, yeah, it's not working. So what is wrong here? When we look at all those steps, we see that we have 4 times recursion from the VPN v4 unicast route 1 to labeled route 2, to ISIS, and then to SR policy, and then to an interface. So that's 4 levels of recursion, right? Turns out that platform, I'm not calling out the platform, but that platform didn't support that, right? So you have to know that the platform and the version of software supports that or not. That's kind of important. But if you looked very carefully, depth 4 could have given you a clue already. 7, still real cases. We have SRLG, shared risk link group. You have multiple links that share the same risk, probably because the fibers are in the same conduit and things like that. So, you know, if you break the conduit, all the fibers are dead. So we give them a color. Usually, we just look at SRLG of interfaces connected to one router. But there is a feature now, specifically in ISIS, with this command where you can advertise the SRLG. So ISIS advertises the color of the links for SRLG to every other router. Great. So now every other router knows the complete topology with the colors of the links. Yes. And how does it work? Well, if there is a failure, we just add penalties. So that's the admin weight that you see there in the middle. So we increase the metric to the specific links to make sure that the backup path is not used for a particular primary path or protected path, right? For the same color. So we don't want a red link on the backup path and also a red link on the protected path, primary path, right? That doesn't make sense. Okay, so we play with penalties and we add that. Customer comes and says, yeah, I did that, it doesn't work. Turns out, the problem is that the customer is using Flex Algo. So here's the default topology, Flex Algo 0, and a Flex Algo which uses IGP metric, and a Flex Algo 128 which uses minimum delay, right? Minimum delay traffic goes Flex Algo 128. Fine. But guess what? That penalty here is 10,000, and for the default topology, you add 10,000 units. Great. But for Flex Algo 128, delay, it only adds 10 microseconds, which is really a small penalty. So in topology 0, protection backup path works. In Flex Algo 128, didn't work. We did some testing, doesn't work. What is the solution? Well, because we use the same penalty for multiple topologies, there's only one solution. You have to increase the penalty to a very high number, 50,000, 100,000, whatever. And by the way, in the latest release, we added some extra flags. One of them is TM, total metric of the backup path. That will help you visualize what is the metric of the backup path. Convergence microloop, that takes some time to troubleshoot. It means the customer looks at convergence when cutting a link. It's a bit slow. Well, 2 things to do. Measure it, use a traffic generator, 1 packet per microsecond, figure out how long is the delay, and look at the drops. And what kind of drops? Are they TTL expiry, routing loops? Are you dropping because of the wrong label, the wrong segment, whatever? That's what you need to do, probably in a lab, not on the live network. SR policy, Another case we had, performance measurement is not working. So we send out probes. We can test a link. We can also send probes for a policy, so multiple hops, and it doesn't work. Now, sending out the probes is a lot of work for the router, so we can offload that to the hardware, to the NPU, and this is the command. That's what the customer does. He says, he comes back, it's completely broken, the measurement is down, the policies are down. And that's because one command was forgotten on some boxes. We have to configure this additional offload 4, which is specifically the performance measurement hardware offload bit that we set. And you have to restart the process, performance measurement, and then it will start to work. Okay? So we got half of the configuration correct. And then the policy and measurements come up. Key takeaways. Any questions on the examples? None? One question?
Are the, let's say, technical requirements per platform, are they there? One idea.
Are the technical requirements platform there? Well, if you use, for example, the show SRv6 manager command, you see them, the capabilities and so on. So that's one way to figure it out. But as always, you're supposed to read the documentation, of course, right? Anything else? All right, so key takeaways. Sorry, just gonna go over 2 minutes. SR-MPLS, simpler than LDP, better protection, and so on. SRv6, long IP addresses, but it works. Micro-SID, compressed form, very nice. And then BGP has to do some extra work to carry the SIDs, for example, for the specific services. All right. I do apologize. I think the slides are in slightly different order. Sorry. The ones you have are the latest one. Everything is fine there in the order as it should be. Finally, if you have questions, you can come up to me now. I'm around forever, so ask me a question or put it on the WebEx. I will answer them in the coming hours and days. And besides that, please fill in the survey. You will probably get a T-shirt at the end, as always. And for that, have a great evening, and thank you.